Hi, and welcome to the 9th section of this course, Collision Detection, Pickups, and Bullets. We'll start this section with coding the bullet class and making the bullets fly. Then we would give the player a crosshair and code a class for pickups. Lastly, we would use the pickup class and detect collisions. Let's now start the first video of this section, coding the bullet class. In this video, we are going to take a look at coding the bullet header file and coding the bullet source file. We will use the SFML rectangle shape class to visually represent a bullet. We will code a bullet class that has a rectangle shape member as well as other member data and functions. We will add bullets to our game in a few steps. First, we code the bullet.h file. This will reveal all the details of the member data and the prototypes for the functions. Next, we will code the bullet.cpp file, which, of course, will contain the definitions for all the functions of the bullet class. As we step through it, I will explain exactly how an object of bullet type will work and be controlled. Finally, we declare a whole array full of bullets in the main function. We will also implement a control scheme for shooting, managing the player's remaining ammo, and reloading. So let's get started with step 1. To make the new header file, right-click on Header Files in the Solution Explorer and select Add, New Item. In the Add New Item window, click Header File, and in the name field, type Bullet. Finally, click Add. Now add this highlighted code. It consists of private member variables, along with the bullet class declaration to the bullet.h file. Let's quickly run through them and see what is happening. In this code, the first member is a vector2f called mPosition, which will hold the bullet's location in the game world. Next, we declare a rectangle shape called mBulletShape, as we are using a simple non-texture graphic for each bullet, a bit like we did for the time bar in Timber. The code then declares a boolean mInFlight, which will keep track of whether the bullet is currently whizzing through the air or not. This will enable us to decide whether we need to call its update function each frame or whether or not we need to run collision detection checks. You can see I've highlighted this line. The float variable mBulletSpeed will, you can probably guess, hold the speed in pixels per second that the bullet will travel at. It is initialized to the value of 1000, which is a little arbitrary, but it works well. Next we'll have two more float variables, mBulletDistantX and mBulletDistantY. As the calculations to move a bullet are a little more complex than those used to move a zombie or the player, we will benefit from having these two variables that we will perform calculations on. They will be used to decide the horizontal and vertical change in the bullet's position in each frame. Finally, we have four more float variables, mMaxX, mNX, mMaxY, and mMinY, which will later be initialized to hold the maximum and minimum horizontal and vertical positions for the bullet. It is likely that the need for some of these variables is not immediately apparent, but it will become clearer when we search for them in action in the bullet.cpp file. Now add all the public function prototypes to the bullet.h file. You can see I've highlighted the entire public function prototype. You'll need to add all this to bullet.h file. Let's run through each of the functions in turn, then we can move on to coding their definitions. First, we have the bullet function, which is of course the constructor. In this function, we will set up each bullet instance ready for action. Next, the stop function will be called when the bullet has been in action but needs to stop. The isInFlight function returns to a boolean and will be used to test whether a bullet is currently in flight or not. The shoot function's use is given away by its name, but how it works deserves some discussion. For now, just note that it has 4 float parameters that will be passed in. The 4 values represent the starting, where the player is, horizontal and vertical position of the bullet, as well as the vertical and horizontal target position, where the crosshair is. You can see float startX and startY for starting position, and floatX target and Y target for target position. The getPosition function returns a float rect that represents the location of the bullet. This function will be used to detect collisions with zombies. You might remember from Section 8, Pointers, Standard Template Library, and Texture Management that the zombies also had a getPosition function. Next we will have getShape function, which returns an object of type rectangle shape. As we have discussed, each bullet is represented visually by a rectangle-shaped object. The getShape function, therefore, will be used to grab a copy of the current state of the rectangle shape in order to draw it. Finally, and hopefully as expected, there is the update function, which has a float parameter, float elapsed time, which represents the fraction of 1 second that has passed since the last time update was called. The update method will change the position of the bullet each frame. Let's look at and code the function definitions. Now we can create a new CPP file that will contain the function definitions. So, right-click on Source Files in the Solution Explorer and select Add New Item. In the Add New Item window, click C++ File, and then in the name field, type Bullet. OK. So we are now ready to code the class. Add this highlighted code, which has include directives and the constructor. We know it is the constructor because the function has the same name as the class. The only thing that the bullet constructor needs to do is set the size of mBullet shape, which is the rectangle shape object, and this code sets the size to 2 pixels by 2 pixels. Next we have the more substantial shoot function. Add this entire highlighted code. Don't worry, we'll run through it. In order to demystify the shoot function, we will split it up and talk about it in chunks. First, let's remind ourselves about the signature. The shoot function receives the starting and target horizontal and vertical positions of a bullet. The calling code will supply these based on the position of the player sprite and the position of the crosshair. Inside the shoot function, we set in-flight to true and the position bullet using the parameters start X and start Y. Now we use a bit of simple trigonometry to determine the gradient of travel for a bullet. The progression horizontally and vertically of a bullet must vary based on the slope of the line created by drawing between the start and target of a bullet. The rate of change cannot be the same, or very steep shots will arrive at the horizontal location before the vertical location, and vice versa for shallow shots. This line of code first derives the gradient based on the equation of a line. Then it checks whether the gradient is less than 0, and if it is, multiplies the gradient by -1. This is because the start and target coordinates passed in can be negative or positive, and we always want the amount of progression each frame to be positive. Multiplying by -1 simply makes negative number into its positive equivalent because a minus multiplied by a minus gives a positive. The actual direction of travel will be handled in the update function by adding or subtracting the positive values we arrive at in this function. Next we calculate a ratio of horizontal to vertical distance by dividing our bullet speed, that is, mBullet speed, by 1 plus the gradient. This will allow us to change the bullet's horizontal and vertical position by the correct amount each frame, based on the target the bullet is heading toward. Finally, in this part of the code, we assign the values to mBullet distance y and mBullet distance x. For mBullet distance y, we assign ratio xy, and for mBullet distance x, we assign ratio xy into gradient. In this part of the code, which is much more straightforward, first we are setting range to 1000. Range is a float type variable. Then we simply set a maximum horizontal and vertical location that the bullet can reach. We don't want a bullet carrying on forever. We will see this in the update function where we test to see whether a bullet has passed its maximum or minimum locations. This code moves the rectangle shape, which represents the bullet, to its starting location. We use the setPosition function as we have often done before. Next we have 4 straightforward functions. Add these 4 functions, that is, the stop, isInFlight, getPosition, and getShape functions. The stop function simply sets the mInFlight variable to false. The isInFlight function returns whatever the value of this same variable currently is. So we can see that shoot sets the bullet going, stop makes it stop, and isInFlight lets us know what the current state is. The getPosition function returns a float rect, and we will see how we use the float rect from each game object to detect collisions soon. The getShape returns a rectangle shape, so we can draw the bullet once each frame. Before we can start using bullet objects is update. This is the code we need to add. I'll explain it. In this update function, we use mBullet distance x, multiply the time since the last frame to move the bullet, and also mDistance y, multiplied by the time since the last frame to move the bullet. Remember that the values of the two variables were calculated in the shoot function and represent the gradient ratio to each other required to move the bullet at just the right angle. Then we use the set position function to actually move the rectangle shape. The last thing we do in Update is to test to see whether the bullet has moved beyond its maximum range. The slightly convoluted if statement checks in position X and in position Y against the maximum and minimum values that were calculated in the shoot function. These maximum and minimum values are stored in mmin_x, mmax_x, mny, and mmax_y. If the test is true, then the mInFlight is set to false. The bullet class is done. Now we can see how to shoot some in the main function. In this video, we have coded the bullet header file and the bullet source file. Cool! In the next video, we'll take a look at making the bullets fly.